Determine all intervals of concave up or concave down and determine the coordinates of all inflection points, including cliffs, for the function f of x equals x times the square root of x minus 3. The first thing to do is find the domain. F of x equals x, a polynomial term, the domain will be all real numbers, times the square root and even root of x minus 3. We can rewrite the square root as a fractional exponent. It will be x minus 3 to the first power second root 1/2 power. The denominator of a fractional exponent is the root. It's an even number here. And the domain of an even root is not necessarily all real numbers. The domain requires that what is inside of an even root has to stay greater than or equal to 0. So x minus 3 has to stay greater than or equal to 0 for the domain. We can solve for x by adding 3 to both sides. And x has to stay greater than or equal to 3. So the domain will start at 3. It includes it and anything greater, so it'll go to positive infinity. The next thing to do is find all candidate numbers. We will need the second derivative for this. We will start with the first derivative. F of x is a product of two expressions, so we will make use of the product rule from the fractional exponent version of f of x. So f prime of x equals the derivative of the first, which is a 1, times the second left alone, plus the first left alone, x, times the derivative of the second, which is a power rule. Bring the power down, leave the inside alone, subtract 1 from the power. I will call that 2/2. And then multiply by the derivative of the inside to complete the chain rule. The first term is 1 times an expression, 1 times anything is that same thing. The second term, we can bring the constants together. 1/2 times 1 is 1/2. There is an x. And there is an x minus 3 to the 1 minus 2, negative 1/2 power. We can take the second derivative right from this version of the first derivative. The first term is just a power rule, and the second term will be a product rule of 1/2 x times x minus 3 to the negative 1/2. So the second derivative, f double prime of x equals, first term, power rule, bring the power down, leave the inside alone, subtract 1 from the power, I will call that 2/2, and then multiply by the derivative of the inside to complete the chain rule, plus the second term, which is a product rule. Derivative of the first, 1/2 x, will be just the constant, 1/2, times the second left alone, x minus 3 to the negative 1/2, plus the first left alone, 1/2 x, times the derivative of the second, which is a power rule, bring the power down, negative 1/2, leave the inside alone, subtract 1 from the power, I will call that 2/2, and then multiply by the derivative of the inside to complete the chain rule. For the first term, we can put all the constants together. 1/2 times 1 is 1/2. And we have an x minus 3 to the 1 minus 2, which is a negative 1/2. Plus the second term, which we'll leave as is. It's a 1/2 x minus 3 to the negative 1/2 power. And then the third term, we can put all the constants together. We have a 1/2, a negative 1/2, and a 1. 1/2 times a negative 1/2. We can multiply the numerators. 1 times negative 1 is negative 1. Multiply the denominators. 2 times 2 is 4. Negative 1/4 times the 1 will still be a negative 1/4. We have an x. And there will be an x minus 3 to the negative 1 minus 2, negative 3/2 power. The first and second terms are both x minus 3 to the negative 1/2. So we can combine those by adding their coefficients. 1/2 plus 1/2 is 2/2, or 1. Times the x minus 3 to the negative 1/2. And then we have the second term, which is negative 1/4 x times x minus 3 to the negative 3/2. We will want the second derivative as a single fraction with all powers being positive and fully factored. We have negative powers for some of the expressions here. We can put them in the denominators of their respective terms, then get a common denominator. That's one option. Or we can factor, since they are the same base. They're both x minus 3. The factoring version is generally a little quicker. So we can factor out an x minus 3 to the lowest power. We have a negative 1/2 power and a negative 3/2 power. The lowest is the negative 3/2. It's more negative. Factoring is division, and division is subtraction of exponents. So by factoring out a negative 3/2 power, we're subtracting a negative 3/2, which is equivalent to adding a 3/2 to each of the powers. Negative 1/2 plus 3/2 will be 2/2, or 1 power. So we'll have x minus 3 to the 1 power left over. Minus 3/2 plus 3/2 will be to the 0 power, and anything to the 0 power is a 1. So there's what we'll have left. X minus 3 minus 1/4 x. So we have an x minus 3 to the negative 3/2. To fully factor, we want to combine like terms together in the square brackets, and we want everything over a common denominator. The third term has a denominator of 4, so we need to multiply the first term by 4 over 4. So it's 4 over 4x. The second term by 4 over 4, so it's negative 12 over 4. And the third term is already a negative 1 over 4x. So we have x minus 3 to the negative 3/2 power. We can combine like terms together. We have 4 over 4x minus 1 over 4x. 4 minus 1 is 3, so we have 3 over 4x, and then minus a 12 over 4. The reason we put the minus 3 over 4, so it's a minus 12 over 4, is so we can now combine the terms in the square brackets with each other over that common denominator. So it'll be, in the numerator, 3x minus 12, and the entire thing over 4. We have a negative power that's been factored out, so it can move to the denominator of the entire fraction. So we will have a 3x minus 12 that will stay in the numerator, and in the denominator there's a 4, and the x minus 3 can move into that denominator and become a positive 3/2 power. The numerator has a common factor of 3. We can factor that out, which will leave behind an x minus 4, and the denominator will be 4 times x minus 3 to the 3/2. So we have the second derivative written as a single fraction. It is fully factored, and all powers are positive. We can now set the numerator equal to 0 and the denominator equal to 0 and solve for all x's. Starting with the numerator, 3 times x minus 4 equals 0. We can divide by 3. X minus 4 equals 0. We can add 4 to both sides, so x equals 4. And now the denominator, 4 times x minus 3 to the 3/2 power equals 0. We can divide both sides by a 4. So x minus 3 to the 3/2 power still equals 0. We can now raise both sides to the reciprocal of 3/2, which is 2/3 power. Because when you raise and raise again, you multiply exponents, and multiplying 3/2 times 2/3, multiplying numerator, 3 times 2 is 6, multiplying denominators, 2 times 3 is 6, 6 over 6 is 1. All that's going to become x minus 3 to the first power. Equals 0 to the 2/3 power. 0 raised to any non-zero power is 0. We can now add 3 to both sides, and x equals 3. We will now check to see which of these are in the domain. The domain is all real numbers greater than or equal to 3. 4 is a real number. It's greater than or equal to 3. 3 is a real number. It's equal to 3. It's actually the left endpoint of the domain. We can now draw a domain line, a line representing the domain. The domain is all real numbers greater than or equal to 3. It includes 3, but we're going to be removing the candidate numbers from the domain line, and x equals 3 is one of the candidate numbers. So when removed, it will remove the left endpoint, so it will no longer include it. So it'll be a round bracket instead of a square bracket. There is no right endpoint since it is positive infinity. We can now put all other candidate numbers on here. We have x equals 4. This splits the domain interval into 2 separate intervals. We can pick a test value in each of these intervals. The first interval is from 3 to 4. There's no integer in there, but 3 is 6/2 and 4 is 8/2. So 7/2 is in there. That's the same thing as 3.5. We also have the interval from 4 to positive infinity. We can pick the test value of 10 in there. We can now test the concavity of each of these intervals by plugging the test value into the second derivative. We don't care about the value of the second derivative, just whether it is positive or negative. The best place to determine this is the fully factored version. That's this one here. Now, a couple things about that. The denominator. The x minus 3 to the 3/2 power. The domain requires that the x minus 3 back up here is going to have to be greater than or equal to 0. And it's only equal to 0 when x is 3, and that's not part of this interval. It's been removed. X minus 3 will stay greater than 0. Now, anything greater than 0 to the 3/2 power will still be greater than 0. It'll be positive. And then times the positive 4 in the denominator will still be positive. That entire denominator is always positive for the entire domain. In the numerator, the positive 3 is always positive, and therefore none of that matters. The only part of the second derivative that matters is the x minus 4. So we can plug our test values into x minus 4. The first test value, 7/2, which is less than 4, it's between 3 and 4. 7/2 minus 4 is a negative. We have a negative second derivative that corresponds to concave down. Plugging a 10 into the portion of the second derivative that matters, 10 minus 4 is a positive. We have a positive second derivative. That corresponds to concave up. So we have concave down occurring in the interval from 3 to 4. Concave up occurring in the interval 4 to positive infinity. Right at the candidate number of x equals 4, we have the concavity changing from concave down to concave up. That means x equals 4 is an inflection point. So we have an inflection point in the x-coordinate of x equals 4 and a corresponding y-coordinate that can be found by plugging the 4 back into the original function. So y equals f of 4, which is 4 times the square root of 4 minus 3, which is 4 times the square root of 4 minus 3 is a 1. Square root of 1 is a 1, and 4 times 1 is a 4. That's the corresponding y-coordinate. So we have one concave down interval, one concave up interval, and an inflection point at 4, 4.